Good morning, everyone. This is Chris Mornitsky with the Fort Worth Astronomical Society. And today, for a change of pace, we're going to be looking at a different star or virtual star party. We're going to be looking at the sun, our very own star. Um, Today, we have clouds, unfortunately, here in Dallas Fort Worth. So it's been rather cloudy and stormy, and we really haven't had a chance to do very many star parties. We really haven't had a chance to do much viewing at all lately. So we're going to do the best we can right now. I do have clouds here, and we have clouds all over the Metroplex. Looks like they're sometimes thickening up, sometimes they're getting a little bit better and clearing out. So we'll do the best we can. We cannot control the weather. So I'd like to welcome everyone from the HEB School District who's watching. I know we have some of our club members, our astronomers out there at your schools, and hopefully you will be able to see something a little bit later today through those telescopes. So in the meantime, let's go ahead and get started. Let's see. All right. So at the center of our solar system, the sun accounts for about 99.8% of all the mass of the solar system. So Earth, Jupiter, Saturn, all the rest of the planets, all the moons, asteroids, comets, all the assorted debris of our solar system accounts for just 0.2% of the total mass. The sun is literally, figuratively, the center of our solar system and of life as we know it. So first of all, what is the sun? Gigantic ball of hot, glowing gases. It's so enormous you could fit over 1 million Earths into it. It's a giant fireball. It's so hot and bright that even being 93 million miles away, it still gives us enough light to see and enough heat to keep warm. So today we're going to see the sun in what we call full spectrum light, as well as hydrogen alpha light. We'll be using special filters that let us see the sun safely. Remember to never ever look at the sun directly without a filter. You can damage your eyes severely. There's only one time you can look at the sun, and that's during a total solar eclipse, like what we're seeing right now. During totality is the only time we can look at the sun. But just before and just after, you can and will damage your eyesight. So never ever look at the sun without a filter. Now, we will have a total solar eclipse. First, we will have actually we'll have two eclipses coming up here in the North Texas area. The first one in North Texas will be a partial solar eclipse on October 14th, 2023. This is on a Saturday. And in North Texas, it will be a partial eclipse. If you go down to South Texas, let's say to the Hill Country, south of San Antonio, over to Midland, Odessa, up to Albuquerque, and then further west, we will have a annular eclipse. So an annular eclipse, we call it the Ring of Fire. The moon's going to be a little bit smaller than the apparent size of the moon will be a little bit smaller than the apparent size of the sun, and so there'll be a bright ring with a dark hole inside. At this time, you can still not look at the sun without a filter. On April 8th of next year of 2024, which is a Monday, we will have a total solar eclipse. And the total solar eclipse, let's wait for the plane to pass. This is one of the hazards of doing star parties from the house, is that we're not too far away from the airport, so there are airplanes flying overhead quite often. Okay, April uh, April 8th, 2024, we will have a total solar eclipse here in the Metroplex. The path of totality covers almost the entire Metroplex. The far northwestern part of Tarrant County will be out of it, but most of the rest will be in it. All of the HEB area will be in it. So at that time, it's a Monday, a little bit in the afternoon, you will be able to go outside and look up and see a total solar eclipse without a filter, only during totality. So at this phase right here, we call this, this is just after totality. We have Bailey's beads. You cannot look at this anymore. You have to use a filter. But during totality, you can definitely look at the sun without a filter. This is the only time to ever look at the sun. So whatever you do, don't do it until April 8th, and then it will be fine. And it is an experience of a lifetime. So back to today's viewing. Um, if we could safely look at the sun, we would see a yellow disk in the sky during the day. But the sun's really white. It's composed of all the colors that we can see. It's the Earth's atmosphere that make it look yellow. So um, the sun is actually white. Let's see. So the scattering of the shorter wavelengths of blue light is what we call Rayleigh scattering. And the yellow gets through, the blue gets scattered, so the sun looks yellow to us. It's also why the sky appears blue to us during the day. So looking at the sun's layers, we have the core. It's just like an onion. The sun has different layers, and it has a core deep inside, just like ours. It's different there. On the sun, we have a very, very hot, very dense center where, let's see. Oh, I need to speak a little bit louder. Very well. Let me see if I can bump up. I really can't. Let's see. A moment. I wonder, okay, if you can hear me a little bit better now. Um, let's see, where are we? Okay, so looking at the core. Yep, mic looks like it's okay. So if it's a little bit quiet, might want to turn it up, but this is as loud as I can really get. Okay. Let's see, so we're looking at the core of the sun right now. Hydrogen there is fusing into helium. It's under a lot of pressure, a lot of heat from that pressure, and so hydrogen turns to helium and releases energy in the form of, well, one-way photons. So the radiative zone just above that is where the photons go and take about 50 million years to travel through that area, being absorbed by atoms and then emitted and reabsorbed and re-emitted over and over again. Then we have the tachocline. The tachocline is it's a transition area between the radiative zone and what we call the convection zone. So the convection zone has hot gas near the tachocline and cooler gas near the surface. So the cooler gas sinks down, the hot gas rises up and creates these big convection cells. The convection cells is how energy goes from the center of the sun out toward the surface. So here the photons bounce around a little bit as well, but not nearly as much as they do in the radiative zone. And the movement of these convection cells up and down create what we call granules on the surface, and hopefully we'll be able to see some of those today. I'm looking right now and it is still cloudy. I don't see anything on the scopes yet, so we'll go on, we'll do our best. So the granulation is the result of these convection cells at the surface. Again, this is getting energy from inside the sun to the outside. And the photons then are able to escape through the photosphere. And the photosphere is the surface of the sun that we see. This is where the light comes from. And so once the photons hit that surface, hit the photosphere, it takes it about, is it 8.5 minutes? Just over 8 minutes from the surface of the sun to reach us here on Earth at the speed of light. So when those photons are created in the core, it takes about 50 million years on average for it to leave the core and come out and eventually hit your eyes. Above the photosphere, we have the chromosphere, which is not on here on this chart. The chromosphere is a region of hot gas, and we'll be able to see it using one of our specialized telescopes. And then above the chromosphere is the corona. And the corona is a region of very, very hot but very thin gas that's being pushed out from the sun. And the corona is what we can actually see during a total solar eclipse. And it's really difficult to see the corona otherwise because the light from the photosphere is so bright that it just drowns everything else out. So we will be able to see that in April. You'll be able to see that with naked eye. It'll appear like this ghostly white kind of um, streamers coming out of the sun. It's very, very pretty. If you had a chance to see it in 2017, when we had the last total eclipse here in the U.S., it was quite nice. It was a very, very good day if you manage to see it. It really is something to see at least once in your lifetime if you can. And luckily, next year we will be able to see it here in Dallas Fort Worth. Okay. So, something strange about the corona. The corona is much, 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 much hotter than the surface of the sun. So, the surface of the sun is about 5,700 kelvins. Um, the corona is actually in the millions of degrees, and we don't exactly know why. We think there's a weird thing going on with the magnetic field of the sun heating up the charged particles in the corona and pushing them out. We're not exactly sure, but scientists are researching it all the time. Um, so the corona is going to be really hard. We're not going to be able to see the corona right now. We will be able to see the chromosphere. So this is just above the photosphere. It's an it's a region where excited hydrogen light is prevalent. This is a deep, deep red color. We can see this with specialized telescopes, and hopefully we'll be able to see um, it in just a little bit. Uh, the light from the chromosphere is deep, deep red. It's from a very few narrow wavelengths of light. You can see it with your naked eye, but the light of the photosphere is so bright that it just drowns it out. So we use special telescopes called hydrogen alpha telescopes that block almost all the light except for this very, very, very narrow band of light. And it is a deep, deep red color. When you look through the telescope, you will see the sun as a deep red disk, but you'll be able to see a lot of details on it that you otherwise can't. So above the photosphere, we have the corona, and we can see the corona with some specialized satellites. We have put up satellites like SOHO, I think, has been up there for 20 years. The Sun Orbiting Helio Observatory, I think is what it's called. Um, Heliosphere Observatory. And what it does is it has a special telescope, and it puts a disk right where the sun is so they can see the outer corona. But we can't really see the inner corona very well unless we have a total solar eclipse. So one of the things that we did in 2017 was actually take images of the corona from the west coast of the United States through the middle and then out on the east coast. And there was an entire project doing this where we took video and and photographs of the sun at different times during this total solar eclipse. We put them together into a movie, and we were able to actually see how that inner corona changed over the was it a couple of hours? Was it a couple of hours? Maybe not even that long. Um, an hour or so? I don't remember. It's been a while. Um, During the time period of when the shadow of the moon hit the west coast all the way until it exited in South Carolina, we were able to make a movie out of that and see the changes in that inner corona. And that was something we had not been able to do before. So it was an interesting project. We'll see if we will go ahead and do something like that again this year, or sorry, next year in April. Okay. And now we're looking at sunspots. So today we're going to be looking at first, hopefully through the white light telescope, and we're going to be looking for these dark spots on the sun. And we can see approximate size of the Earth. that these are very, very large. The Earth could fall into one of these sunspots very, very easily. So these are cooler areas of the sun. They are still very, very hot, but they appear dark to us because they're cooler than the area around it. So we know what they're caused by. They're caused by the magnetic field in the sun coming out in a loop from the surface. So sunspots always happen in pairs. There's a positive side and a negative side where the magnetic field lines come out, loop, and then come back in. And the reason why they're cooler is a neat physical technique that we use for cooling gases on Earth, but it's called magnetic cooling. So the quick version is this: atoms have a temperature, and the temperature is dependent on how much energy they have. And the more energy they have, the more they move. So if you stop those atoms from moving, their temperature drops down. So atoms move everywhere, left, right, up, down, backwards, forwards, in all directions. But if you put a charged atom inside of a magnetic field that's really, really, let's say, straight. So if you have a big magnet with a positive side and a negative side, and the field lines are going in between, and you put a gas in there that's charged, normally it would move in all directions, but the magnetic field lines keep it constricted, so they can only go backwards and forwards. And when that happens, the temperature of the atoms, or the gas as a whole, drops. So this is what's happening in the sun. Those the atoms, the gases, the plasma in this case, the charged particles are not able to move as quickly or in all directions. And so when you restrict the temperature, or restrict their movement, the temperature drops down. And to our eyes, these sunspots appear to be um, dark. If you were right above that sunspot, it would still be glowing very, very hot. So you wouldn't necessarily notice that you were above a sunspot if you were directly over it. But if you compare the size of it to the size of the Earth, you would be very, very, very small indeed. Have a jet flying overhead. Wait for just a moment. Uh, Now, one of the interesting things about about sunspots and these magnetic field lines is this is where we see stuff like prominences and flares. And these are big eruptions of gas exploding off the surface of the sun. And they look something like this. So we have the sunspots, and this is an actual image of it rotating around the sun over several days. This is the current view of the sun right now. This is what we're seeing. So the sunspots get names, well, really numbers. And the numbers are based on the activity cycle of the sun. So every 11 years, the sun goes through a cycle where it has more activity and less activity. And we define that by how many sunspots it has. So when the sun is quiet, the magnetic field lines are relaxed inside the sun. They're inside the sun for the most part, but the sun rotates differentially. So the middle rotates faster than the poles. So the middle latitudes, like around the equator, and when that happens, the field lines get wrapped around and around and around the sun. Eventually, they get so tight, I guess we call it, that they can burst through the surface. And when they do, they create sunspots. They also create prominences, and you can have flares, which are massive explosions on the surface of the sun. They can throw out material into the rest of the solar system. We call these coronal mass ejections, CMEs. And these are dangerous for our satellites. Um, they're charged magnetic particles, and they can interfere with the way satellites work. They can damage satellites to the point where they're no longer working. So we don't necessarily like them. We haven't had a very, very large CME that hit the Earth directly in a long time. There was an incident in the 1800s, and we think there was a huge flare that went off and hit the Earth directly. And we have records that um, the telegraph lines were highly uh, electrified to the point where people were being shocked when trying to use the telegraph. Um, there were fires caused by it because there was so much power going through these telegraph lines. There were huge auroras, which is another side effect of these coronal mass ejections, where we have auroras at the North Pole and at the South Pole. And there were huge displays that could be seen very, very far south because there was so much energy, so many charged particles being dumped into the Earth's upper atmosphere, trapped by our magnetic field. So we're coming up in the solar cycle right now. I think the low point was 5 years ago, so we're almost at the midpoint. So it goes down, comes back up, and goes back down, and it's that up down or down up down period, which is about 11 years. So we're gonna hopefully be able to see this today. I was able to see some of these earlier when the sun came out. But right now looks totally clouded over. This is a prominence on the sun, but we're speeding this up by a lot. I think this is sped up about 300 times or more. Uh, Actually, it's probably closer to 1,000 times right now. So what's going on right now is we can see these magnetic field lines pretty well. Every one of these lines here, these are what we call lines of force. And they're glowing because there is gas that is traveling right along those field lines. So it's erupting from the surface at one point, traveling over, and coming back down to the surface at another point. If there is enough energy, this can also throw material out. It doesn't just loop out and come back in, it throws it out completely. The magnetic field lines can be so powerful, they just throw material out. And we call those the one type of coronal mass ejection. It's one of the problems with doing this outside is everyone outside who may be mowing their lawn or flying an airplane or driving by can hear all of that. I think that was actually an airplane taking off. There's an airport not too far away. So back to the sun. What we're seeing here is this prominence. We have another prominence out here. Today, when I was looking earlier, I could see several prominences and possibly one or two flares on the edge of the sun. Will Right now it is completely cloudy, so I don't actually have anything to show. Um, Going back to this, we can see it getting a little bit bigger, but falling apart. And this is over a period of hours. Oh, and by the way, we go back. Just looking at this, our Earth got that big, a little bit bigger than this loop down here at the bottom. So our entire world can fit underneath this loop with plenty of space around. And that's something to think about on the scale of the universe. We think we're big, we think we have a whole planet, but just comparing the size of the Earth to the sun, even small features on the sun, we're not that big. Uh, our planet's we call it a small rocky planet. It's the largest of the rocky planets in our solar system, um, but it is small in comparison to the gas giants, and very much small compared to the sun. It even features up on the sun. So let's see. Continue on. Watch it go through yet again. And this is from one of NASA's solar orbiting observatories. So we can do this kind of stuff now. We can send up a satellite and have it observe the sun continuously for long periods of time. This is not a satellite that orbits the Earth. This is a satellite that actually orbits um, the sun. We push it far enough away from our world that it is constantly around the sun. We don't have to worry about it uh, going behind the Earth, not seeing the sun anymore, um, not getting enough power to the solar panels. We push it out far enough away. It is now in its own orbit around the sun, relatively close to the Earth, but it sends us signals and shows us exactly what's going on. We can see the sun 24 hours a day, 7 days a week, 365 days a year, and we can gather that kind of data. Some of the sensors are um, can see in hydrogen alpha light. Some of them see in calcium, potassium. Some of them see in ultraviolet. So we can see the sun in various wavelengths that let us get more details about what's going on, and we can continuously monitor it. So we want to know things like, is the sun setting off a coronal mass ejection? Is it giving us a big blast of high energy particles? Uh, do we have to worry about that now? Because if that is happening, we can take precautions. Is it hitting us directly? Well, that's not a good thing. Well, what can we do? Well, we can shut down satellites. We can put them into like basically a sleep mode so that their circuits aren't overwhelmed. We can do things like on the Earth, we can also power down certain things. We can take precautions on power lines. Power plants can take that into account so that we don't have blackouts and brownouts and destroyed equipment. There's all sorts of things that we can do if we know something is happening um, ahead of time. And usually with a coronal mass ejection, we probably have uh, days, if not a couple of hours of notice that we can plan ahead. That's all we can really do. There's no way to stop it. Okay. Remember, these things are very, very large. They're traveling pretty fast, and they're much, much bigger than the Earth. So we can't block it. We can't stop it. All we can do is prepare for it. And if we do get hit by a coronal mass ejection, well, at least we can have some really pretty aurora that we can see. Rarely can we see them down in Texas. There was one was it back in, I want to say this was back in March or April. We had a small solar storm that hit us. However, we had clouds at that point. So the aurora, it was deep red, and you could see it very, very low on the horizon to the north. But um, we had a lot of clouds, and we could not see it here from North Texas. So maybe another time. All right. I'm going to. I'm going to switch over to here. Let's see. Okay. I have two telescopes with two cameras, and I'm looking to see if we can see anything. This is the uh, this camera is the white light camera. This is all I have. It is cloudy enough that I cannot see anything. Um, there's a big thick cloud, so I'm not sure what we can do right now. There's a big thick cloud. This is a 1 second exposure. Um, and I'm really not able to see anything right now. So let's look at the other camera. This one is specialized camera. Maybe we'll see something. No, got nothing. Got nothing on both cameras. There's enough clouds right now that that we have nothing. So right now, I think we're going to have to stop the stream. There's not much more that we can do. I think we're going to have our astronomers go out and see if there's anything that you can see through the telescopes out there. I wish I could show you more, but it is completely cloudy right here. And the clouds look to be getting a bit thicker too. So unfortunately, I think we're going to have to stop our stream. Um, I'm kind of sad about this because I was really hoping that we could see some stuff. I'm just not able to see any anything really. We should be able to see at least the disk of the sun, but the yeah, the clouds are so thick that I can't even cut through them at all. Let's see. We'll do just one long exposure, see what we can see. But no. Well, that's what I have. I have a fuzzy thing. This is not going to work at all. Let's try this camera. No. We'll do one more. Try a 4-second stream. No, 4-second exposure. We have clouds. So, yep. This is a 4-second image, and all we have is clouds. That's the way it goes sometimes, though. So if the weather is good, the weather is good. If the weather is bad, the weather is bad. And there's nothing we can do about it. It was okay just after sunrise, but right now, it is not. Okay. Um, Unfortunately, I think that's it. So uh, I'm going to go ahead and sign off. I hope that you guys are going to be able to see something with the telescopes. I hope you learned a little bit this morning about this, about the sun, about the eclipses that are coming up, and might have to do this again and try again and again and again until this works. So, uh, good morning, everyone, and I hope you have a very good day. And I hope the clouds clear up a little bit so you can actually see something outside with the telescopes. And thank you.